Our next question is, I'm sorry, did I cross a line? How can we make predictions about future or unknown data using a very simple model? And what we're going to do is we're going to assume that we want to build an incredibly simplistic model for doing predictions. Well, here's a way where I could maybe try and make some predictions about some data. I have some data set, and if I look at the data set, I can compute the median, and the median of this data set is 29.98, and I could say, I know how this data was generated. I know the process. I know what's happening in the real world. And so I'm going to use a point estimator. I'm going to estimate that most of the values are going to be 29.98. They're going to be clustered really close around the median. Maybe I even have the median and maybe another descriptive statistic as well. Well, if I were to say, I'm going to guess that every value is at one specific point, 29.98, I could measure how good of a guess that was by creating some sort of error metric. And my error metric could be take where the actual underlying data values are, minus what my guess is, square that, call that some error, some residual, and sum it up. And so you can see that's my sum squared error given this simple metric. And what I could say is, if I wanted a point estimate, if I wanted one single value as the best guess for what this data is, well, what I could do is I could construct a bunch of candidates, a bunch of possible candidates for this value, and I could just use an argmin to find which one minimizes this error. And if I did that and then mapped it back to the original data values, I could see, 30.03 minimizes this error as a point estimator. And if you remember, we have just rederived what the mean is. The mean is actually a point estimator, a single value estimation for the data that minimizes particular error, and the median is an estimator that minimizes a different type of error, not the sum squared error, but the absolute value squared error. And you can think the mode is another. It's like a one hot. It's a binary 0-1 estimator for this. Well, instead of a single value, what if I want to say, I know about lines, I've used lines my whole life, y equals mx plus b. I want to see if this data maps to some sort of linear relationship. So far, much of what we've talked about presumes linear relationships. And so what I'll say is y, the value that I'm guessing for something that I can't observe, some future or unknown data, is related to x, the data that I do observe, via a linear relationship with constant a alpha and with some coefficient beta. And given that, I can say what my error would be is just what my guess is minus what the actual observed values that I see if I have some training set or testing set. Well, I can use that in order to try and figure out, well, what's the best value of alpha and what's the best value of beta? And largely, my approach for finding that is not too dissimilar from my approach for finding what that point estimator is. I'll just come up with some cost function, some error function, and I'll try and minimize it. That's all I'm doing when I'm doing argmin. I'm just computing what the sum squared error is. I'm just trying to find where is it smallest and say, well, that's the value. And so what I could do is I could say, let me try every alpha from 0 to 5, stepping by 0.05. Let me try every beta from 0 to 5, stepping 0.05. Here I'll create a set of candidates with my mesh grid formulation. I'll take those candidates, and what I'll do is I'll say, use the alpha and use the beta, subtract it from the observed resulting values. This is my guess. This is what I actually observed. Take that error, square it, and sum it up, and then give me the argmin. And when I do this, it's a little bit slow. Let's go up a little bit. It's a little bit slow because we're going to search through this whole space, but it'll give me its guess that the alpha parameter, probably 2.05, and the beta parameter, 3.5, at least to minimize this. Now, I can mathematically compute this. Here, what I'm doing is what's called a linear regression. I'm trying to figure out what the optimal parameters are for the coefficients in a linear equation, that alpha and that beta, or if you're familiar with y equals mx plus b, the m and the b parameter. And for this simple one-factor linear regression, I can actually directly compute these. I can compute the best beta as just the covariance divided by the variance, and the alpha as just whatever the beta is minus the mean of one minus the mean of the other. And you can see my two formulations actually match up quite nicely. You can see my very simple brute force search matches up almost exactly to the value that I can compute by hand. And what I'm looking for is, with the best value of alpha and beta, then every one of my guesses should be close to every one of my actual observed values. And I might have to give this a little bit of a threshold depending on how close of a fit that is, and we'll be able to quantify that in a moment. Now, if I wanted to do this properly, instead of computing it by hand like this or computing it with this very inefficient search, I might do a linear regression using scipy.stats, and it gives me the slope and the intercept, and these tie out to the previous values that I saw exactly. Now, if this is a very good fit, you can think that what that means is, given the slope and this intercept, every guess I would have should be very close to every actual value I have in both my training set and actually when I deploy this to the real world. If it's not a very good fit, then I will see that they're not all close. And a question might arise, can we quantify how good of a fit this is? We can, and this is what we talk about when we talk about things like correlation coefficients and R squared. Let's take a look. You may hear people talk about things like the coefficient of determination. Here's the case. I have some data. I am going to create a data set that is clearly linear related to this data set with just a little bit of noise. It's basically, look, the alpha parameter is basically 3 and the beta parameter is pretty much 2, which is a little bit of noise to make it imperfect. And here I have another data set that is completely unrelated to the first data set. There should be no relationship. For the two related data sets, I can compute using my scipy.stats.linregress the slope and the intercept, and that will give me, in addition to the slope and the intercept, an R value. And this R value is what we call the correlation coefficient. This R value gives us the ability to say things like, or at least the R squared value gives us the ability to say things like 30-something%, or in this case, this value squared, that percent of the variance that we see between our guesses and the actual values is explained by this particular line. And so it's quantifying how close that line is to the values. And we can see how to compute it. It's a fairly straightforward and fairly obvious computation for this R value. What we would do is we compute what we might call the residuals. It's basically the error. What we would compute the values to be using these two coefficients minus what the values we saw are. And we just find what the variance of the residuals are scaled by the variance of the underlying values we saw, subtract 1 from that, and that gives us what we call R squared, the coefficient of determination. And if we take the square root of that, that takes us back to what this R value is. That gives us this correlation coefficient. In truth, all this is really doing is just saying, if we drew a line using those coefficients, what's the variance of the underlying values that we saw, the actual values that we saw in our training set, against where you predicted them to be? And how can you summarize that? It's just a summary for those values. Now, you might wonder why it's called the correlation coefficient, but you can see things tie together quite nicely if you consider that what we're doing is we're taking our guesses, just the alpha that we guessed against plus the beta we guessed times the values that we saw. We're taking the actual values that we saw in our training data. We're computing our error by just looking at the distance of those. We're computing not our error, but our mean squared error by looking at that error squared and the average error. If we take 1 minus the mean squared error scaled by the variance of the values that we observed, that's just R2, your coefficient of determination. If we take the square root of this, this is just your correlation coefficient. In fact, this correlation coefficient, this R value, is just the correlation between what your guesses were and what your actual values are. That's why the correlation was useful. Even though we might not be able to use it to predict something, if we're convinced that there is a relationship and want to figure out how to model that relationship with a simple linear model, we can use the correlation coefficient in order to quantify how good of a fit that model was. And so you can say, oh, my model had an R or an R squared of 0.99. Sounds like a pretty good fit. In fact, we can say this particular model accounts for 99% of the variance between the guesses and the actual. And that sounds pretty good to me. Now, just like with the Spearman rank correlation, we can get a p-value for our linear regressions. And you can see here the two p-values. For the two that are related, you can see it's a very small p-value. For the two that are clearly unrelated, it's also a surprisingly small p-value. This is why we have to be a little bit delicate when we use this frequentist statistic null hypothesis rejection approach. But anytime we have a p-value, we should always think back to what's the null hypothesis, what's the alternate hypothesis, what's the test statistic, and what's the distribution. This p-value for linear regression is an assumption that, or is testing the null hypothesis that the slope of the linear regression is 0, meaning there is no linear relationship. And our alternate hypothesis is that the slope is non-zero, that there is a linear relationship. Now, this is a two-sided test. We can do one-sided tests that it's a positive correlation or a negative correlation. But setting that aside, we can take what our p-value is, and we can see that it's all it is some test statistic that we compute by taking the Pearson correlation, it's some test statistic computed using what's called a Wald test that uses at its basis the Pearson correlation. And it's really just that applied against a t-distribution. And since this is a two-tailed test, you multiply it times 2, and there you go, there's your p-value. We went all the way back to computing this p-value from scratch. And in every case that we're doing one of these statistical tests, it's always the case that we should think about it in terms of what is the null hypothesis, what is the alternate hypothesis, what is the test statistic, and how do we construct it? Here we use this Wald test statistic. And what's the distribution that we're going to test it against, and that allows us to identify what's the probability of lying in that so-called critical region. But why do we care? Well, we care because if it were the case that we were definitely certain that there was a causative relationship between two variables, we have some data that we observe, and we have some data that we want to know about, and we know there's a linear relationship between them. We know there's a causative relationship. We can then build a model for that relationship. We can then figure out what the parameters of that linear relationship will be, and we can use that to predict values. And so our approach here, our linear regression approach, what we might call our ordinary least squares linear regression approach, we'll talk about why we call this ordinary least squares, is one of the simplest models that we can use to directly be able to predict values that we cannot observe future values or unknown values. But it does, assume that there is a relationship here, and it does make certain assumptions about the underlying data, namely that there are normal distributions here and that there is a constant variance. But we'll mention that as well. But really, at its core, why we care is a linear model is a very simple, very easy to interpret model that allows us to directly and immediately make predictions.